Division at the Library of Congress. Today's program is about Dayton C. Miller, a flute player, flute maker, and scientist, and Claude Laurent, a flute player, flute maker, and clock maker, and how Laurent's 1806 patent connects them and has brought all of us here together today, over 200 years later. We will also hear a performance on one of Laurent's flutes, followed by a discussion about materials and sound when science meets music. The first question, who was Dayton C. Miller? Miller was born in Ohio in 1866 and grew up playing and making flutes. He studied astronomy, acoustics, and physics, and was physics professor and chair at Case Western for over 4 decades. Also, for 40 years, he collected flutes and flute-related materials, documenting the history of the flute. He amassed an extraordinary collection of books, music, art, and documents covering every event, invention, publication, and personality related to the flute, along with nearly 2,000 flutes. Dr. Miller intended to bring his entire collection, tens of thousands of documents and objects, to the Library of Congress and to be its honorary curator, but he died suddenly while packing up the collection. The Miller collection arrived here in the year of his death in 1941, and I am honored to be its curator today. The Miller collection flutes are from all over the world, from many different makers and of many different materials, including 20 flutes of glass or crystal from the workshop of Claude Laurent of Paris. Did Miller focus on collecting crystal flutes by Laurent? Yes. In 1905, Miller bought his first Laurent flute. It's number 11 in his catalog, which is in order of accession. And the flute was made in 1844 in Paris. Of the first 10 flutes in the Miller collection, 2 were his childhood flutes. One was actually in his playpen with him. he noted that. 4 were made to order by Miller, and 2 were made by Miller, 1 in silver and 1 in 22-karat gold with 18-karat keys. And that flute is on exhibit in the Woodhall Pavilion next door. With the purchase of the Laurent flute, Miller now had and had played on flutes of wood, metals, and glass. The 1905 purchase of the Laurent flute may have piqued his curiosity about materials and sound, because by 1908, he had developed a scientific instrument to photographically record sound waves. He named it the phonodike, meaning to show or exhibit sound, and he used it to test on his own flutes of wood, the metals, glass, or crystal. Among his many publications on the flute are his 1916 book titled The Science of Musical Sounds, and a 1925 paper on flutes of glass, in which he stated he knew of 25 crystal flutes by Laurent around the world, and that he, Miller, had a remarkable collection of 5 of those flutes. But Miller was clearly captivated by them and their maker, and he would go on to obtain 20 flutes from the Laurent workshop. So who was Claude Laurent? Laurent was born in 1774 in Langres, a small town in the northeast of France. He enjoyed flute playing enough that flute music was dedicated to him. He earned a living as a mechanical clockmaker and turned to flute manufacturer by 1805. For over 40 years, he made flutes of wood and glass until his death in 1849. He was very successful at flute making and marketing, as we shall see, and obtained 2 patents related to their manufacture. Did anyone ever make glass flutes before Laurent? And 2 early sources say yes. The earliest source references Henry VIII, King of England, from 1509 to 1547, who was also a renowned flute player. Upon his death, the inventory of his wardrobe lists over 100 flutes and recorders of wood and ivory, as well as 3 flutes of glass. The next reference, about 100 years later, in 1648, is in Marin Mersen's Harmonicorum. Mersenne was French and well known for his scientific studies in acoustics, math, and music. This rare and monumental reference book on music and musical instruments in the Miller collection describes flutes made of various woods that are easy to work with, but also mentions flutes made of glass, crystal, and even wax. This might indicate that flutes made of wax and crystal and glass were less easy to work with, and also that there is a distinction between glass and crystal. I'll leave that to our panel to discuss later in today's program. But the use of glass as a material for modern flutes belongs to a few makers in Paris, notably Claude Laurent, his apprentice and successor J.D. Breton, and a little-known maker named Charlie. All three makers are represented in the Miller collection. So why did Laurent want to make a flute of crystal? He was mechanical, clearly, a flutist, or a frustrated flutist. He was seeking a perfect flute, an object of beauty with a sonorous sound that was not disturbed by the effects of humidity or temperature that commonly plagued flutes of wood and ivory of the day. Interestingly, he grew up in an area of France well known for glassmaking. By the end of the 18th century, he was making and selling luxury clocks in Paris and would have been aware also of the Paris expositions, possibly exhibiting at them with his own clocks. And apparently, he thought he had a remedy for those frustrating problems to try crystal as a material for his perfect flute. Since crystal is hard to work with and more expensive, he made the flutes in sections versus one long tube. He added silver for the sockets, the tenons, and the keywork, and for captivating musicians and the audiences, he decorated the caps with rock crystal, colored glasses, mother of pearl, topaz, and sometimes he studied the keys with gems as well. Or he would add trace elements to the tubes, and that would add colors such as blue and green. So how did he get to the 1806 patent? First, by June of 1806, he had perfected his crystal flute enough to submit it to the Imperial Conservatory of Music, who then showed their report to the imperious Minister of the Interior. This report stated that the crystal flute, of which Laurent was the ingenious inventor, was preferable to various flutes of wood and ivory. By September 8th, the crystal flute was examined by the Athenaeum of the Arts, who tested it by playing it under various conditions of humidity and dryness, and even subjected it to the heat of a fireplace. They also judged the sounds of the crystal flute, and they recognized in a congratulatory report that in comparison to ordinary flutes of wood and ivory, first, that the tubes were perfectly well drilled and rounded, that the tone holes were more perfect, that the sounds of the flute were more pure, more equal, more brilliant, and that the cold, the heat, and the humidity and the dryness do not alter the accuracy of the sounds. Their conclusion was that it was a perfect instrument, although it would be more perfect if Laurent could lessen the weight, which he did, and in every point superior in elegance, beauty, and quality, and that composers and lovers of music must hasten to obtain one, and many did. And then there's the patent. By September 10th, he submitted the patent for a flute en cristal, some of which you can read in your program, which stated he had been searching for a long time the means to remedy the alteration that all flutes experience due to humidity, which is the player's breath, and dryness when you put it down and you're not playing it. And also wanting a perfect purity of sound, he found that crystal was the proper material for purity of sound, inalterability of intonation, and ease of playing. His invention, his patent, was for a flute of crystal. He was now a flute maker, and today we know of 185 extant flutes by Laurent. As you will also note in your program, today marks 214 years to the day that Napoleon decreed there should be a fourth Paris Exposition. The 1806 Paris Exposition was a huge opportunity for Laurent. The idea of the Paris Expositions was a formal display of French products, and to give a prize to the product that was deemed perfected. Any citizen could apply to be an exhibitor, even if you were in jail, and the awards were in the form of a medal, prize money, or an honorable mention, and as a consequence, awardees saw a rise in their reputation and orders. The first public expositions of 1801, 1802, and 1806 were called the Napoleonic Expositions, and he would spend hours touring the displays and the booths and asking questions and examining the products. Some exhibitors, of course, presented Napoleon with one of their products. This attention and the prize money encouraged She might want to come back when the flutes are being played. It'd be very pretty. This attention and the prize money encouraged competition and more inventions, as it was hoped, and with each exposition, the number of exhibitors doubled from the previous one. By the time of the 1802 exposition, even foreign visitors were invited, and the British were welcome at that point. The 1806 Paris exposition ran from September 25th to October 19th, which was about 2 weeks after he submitted the patent application. And it was so vast that it was moved from the Loew to Les Invalides and was judged by the most illustrious academics of the day. This exhibition was notable in that it raised the perception of beauty in the arts and helped put French products and demand for them in the world market. Laurent won a silver medal and an honorable mention, and soon, armed with a patent, superb craftsmanship, and clever marketing skills, he would place his crystal flutes around the world by giving some of them away. Such recipients included Napoleon, his nephew Louis Napoleon, a president of the United States, emperors and kings, to name a few. They were also bought and treasured by famous flute players, composers, wealthy amateurs, and collectors. His flutes were in such demand that by 1847 he had 5 employees in his workshop and an annual turnover of 30,000 francs, which in my rough math is about $186,000 today. Speaking of today, they are sold at auction and remain highly regarded for their artisanship, their beauty, their stories, and their histories. Even the cases are uniquely beautiful, and they were likely costly as well. Laurent's successor, Breton, would go on to exhibit flutes at the Paris expositions of 1844, 49, 55, and 67. And at the 1855 exposition, Breton's flute sold for 1,500 francs, which is about $8,000 today. And at some point, Breton was reportedly exporting 90% of his musical instruments. Speaking of stories and a president, there was one Laurent flute that was Miller was particularly proud of having obtained, and that's flute number 378. It's of crystal. It was made in 1813, and it was inscribed on the silver ferrule, and I'll translate from the French. Presented to His Excellency James Madison, President of the United States. After Madison died in 1836, it went to Dolly Madison, who then gave it to her son, John Payne Todd. He bequeathed it to his doctor, who then left it to his children. And in 1923, Miller, after trying for quite a few years to get this flute from their hands, they actually sold it to him for $200 plus $3.20 in shipping, which is, he noted all of this. He's an incredible collector, which is about $3,200 today. We know it stayed with Dolly Madison. She took it when the president's house was being burned, so it survived that, and it stayed with her because there's this remarkable letter in the Dolly Madison papers at UVA. We have the James Madison papers here, but at UVA there's a letter from Thomas Ludwell B. Brent, where he states, and he was in like Flint, Michigan, and I think he was very cold, how I should like to be in Washington this winter and play for you upon that sweet crystal flute. So now you're all curious, what do they sound like? And that is a question we hear all the time. And so we are thrilled to have with us today Richard Graef. He is a flutist, a flute collector, a player on historic flutes. He's been with the Chicago Symphony for over 40 years. He just retired, while also teaching at Northwestern, Indiana, and Roosevelt universities. Richard is going to come out on stage, and he's going to play on 3 of his own flutes of different materials. They're also from different time periods, but this is just more for you to listen to the sounds of flutes of wood and crystal and gold. Similar to what Miller did with the phonodique experiment, that was a visual test. This is one of sound, and it's your own subjective, what do you like, what do you think? And you can shut your eyes and see if you can figure it out. And after that, he's going to play a few pieces that he will announce from the stage. So I'm going to turn it over to Richard.
So I will be playing 3 different flutes. Did Carolyn tell you this already? Yes, okay. I'll be playing 3 different flutes, one wooden, one crystal, one metal. We're asking you to close your eyes, no cheating. And let's see if you can identify the instruments. Open. Number 1. Wood, crystal, metal?
Wood. Metal.
How many say wood? Crystal, metal, is wood. That leaves 2 choices. Number 2, metal, crystal. You got it, crystal. Number 3 was metal. Good, all right. It's interesting because they all are similar, but you should hear that they're really designed at different time periods. The wooden one that I played is a late 18th century flute. The Laurent crystal is 1819. The metal flute was 1983 when it was manufactured. The piece that I use for demonstration is actually a charming Swiss folk song. Can you hear me all right, by the way?
Yes.
Good. Is a charming Swiss folk song called Ariete Freut euch ins Leben des Lebens, which means in English, Ariete, enjoy yourself in life. In other words, live it up. And it's a charming little piece. I'd like to play the complete little folk song with one variation on the Laurent flute. words also say, pick the rose before it withers, but look out for the thorns. I'm joined today by my children, Julian Graef and Anita Graef. I play with Emily Graef, my wife, also flutist, and myself, frequently in the Giuliani Ensemble. We just did 5 concerts in the Chicago area, and they indulged me. All 5 of them were built around the crystal flute. So we've had a busy, that was all the month of December. So the next piece is the first movement, an andante movement of a very beautiful duet by Carl Philipp Emanuel Bach, the son of the famous Bach, written for violin and flute. This is by a relatively unknown composer, Nicolo. He was a Frenchman, worked most of his career, however, in France. We will do 2 movements of the sonata, an adagio movement, a slow movement, then followed by, I think, a very charming allegretto movement for the 2 instruments. This is by Francois Devienne. Devienne was the first, actually the first ever professor of flute at the Paris Conservatory in the very late 18th century into the early 19th century. His music was very popular. He was often sometimes referred to as the French Mozart. It's music that would have, in his time period, clearly have been played on the Laurent crystal flute.
panel on music meets science. I'd like to introduce my panel, Richard Graef, as you know. Richard, come on up. Dr. Lynn Brostoff, research chemist here at the library in the Preservation Research and Testing Division. And Dr. Murray Loew, chair of biomedical engineering at George Washington University. So Richard, you're up first. What is it like to play on a Laurent flute, and is it heavier?
Is it heavier? In many ways. It is heavier. It's heavier, certainly heavier than the older wooden flute. It's only moderately heavier than the modern day metal flute. The distribution of the weight is considerably different. There's more weight toward the blowing end of the flute than the fingering end of the flute.
So Laurent did try to lessen the weight by, on the outer part of the tube, he cut away at the crystal in what we call flutings that are here, and sometimes he did it in a diamond faceted pattern, which is quite stunning. Why did you collect your Laurent flute? Why do you collect flutes? How many Laurent flutes do you have? You need to know this.
I'm actually compared with Dayton Miller, a very minor collector. I have maybe 35 or 40 flutes. The Laurent crystal flute, which I'm very blessed to own, is certainly the centerpiece of my collection. I have learned to play, and I teach a course in playing the traverse of the Baroque flute, which was the flute of the 18th century, which predated the Laurent crystal and the changes which happened going into the 19th century. I started collecting many years ago when I was living in Minneapolis. I was in the Minneapolis Symphony, and I went to a garage sale. And at the garage sale, in addition to all the old baby clothes and other things you expect, there was an older flute, an older wooden flute. And so I pointed to it, and I said to the woman, I said, "What do you want for that?" She said, "That old clarinet?" She said, $250. And I thought, does she mean 250? So I thought about it, and I said, "Okay, will you take $2? And she said, "Yeah." That was the beginning of my collecting.
So what do you think about the perfection and the beauty of it?
It's a remarkable flute, and I think it's been a flute that has been misunderstood greatly. The early 19th century was a time when music was changing dramatically, and the older flute of the 18th century with 6 finger holes of one key simply did not keep up with the demands the music was making. The flute needed to be more evenly projected in all of its notes, and it needed to have a certain sound, a certain sizzle, I like to call it, a certain life in its color that would project well. Laurent was the genius who figured out that could happen by changing the material, and he chose crystal glass. And as I hope you heard, it has a ringing, beautiful quality, which is absolutely unique to the Laurent flutes, and I think is very appropriate, especially for the music of the first third or half of the 19th century, which was basically what we were playing for you.
Mm-hmm. Yes, it was great. Lynn, I'm going to turn to you now for a second. So Laurent's patent was for flutes en cristal. What is crystal?
Yeah, we were very inspired by Richard's title for this event. It really made us look back at the patent in a way that we had not looked at before. And 2 words in that patent are very important, as I have up there on that first slide, en cristal. And crystal, I think if we did a poll in the audience right now and asked you, what is crystal, we would hear many different answers. And crystal as a term is used very loosely for many types of materials today as it was back in Laurent's time. And it's interesting to look very in depth at this because it's such an important part, this material that he used, as Richard was just pointing out, and that he chose. Obviously, one of the important aspects of the material was that it would not change dimensionally with heat and humidity so that the tone would be preserved. And we, as well as many people, because we know of this patent, think of these flutes as made out of crystal glass, which to many people in the museum world and also in the glass world means high leaded glass. And that means actually over 24% lead oxide. So it's a very specific kind of recipe for glass. And when we were first beginning to study these flutes, Carolyn and I started looking at them with different types of analytical instruments. And that part of the study, the technical study of the flutes, will be discussed more by Dr. Loew. But as an introduction, I would like to tell you that we nearly fell over when we started analyzing these and discovered that a few are made of exactly what we expected, high leaded glass, but most of them are what we would call potash glass, which is a completely different type of glass, and in fact is completely non-leaded. There's no lead at all. So this actually shocked us, and many people who have found out about this, who have these in their collection, are quite surprised. And so to understand, okay, well, what did the patent mean, and why did Laurent make these flutes out of two different types of materials? In fact, I thought as an introduction to the technical study, I would just do a whirlwind tour of the history of glass and how the term cristal came up and what it has meant over time. So originally, glass, which is a man-made material, which is totally amorphous, meaning that the atoms are just helter-skelter and no kind of pattern, was often, most often, tinged with color because of impurities in the raw materials that glass is made out of. And most of that glass, over history, was what we call alkali silicate glass, and that's because alkalis are used to lower the melting temperature of the silica, which is important to make it. Rock crystal is a completely different material. In fact, it is crystalline because it is a natural mineral. It is truly, the atoms are in a regular arrangement. And it's very beautiful, and over many centuries, and it's still today as well, carved into beautiful objects, and they can be as beautiful as diamond, glittering and very clear. Well, this is a very expensive process, and these are very dear items, and the world was really hungering for another type of material that would be clear and sparkly like rock crystal. And those clever Venetians at the beginning of the Renaissance came up with an artificial type of rock crystal, which they called cristallo. And cristallos, this doesn't mean crystal per se, it means this clear kind of body of glassware that they were making. And this stuff became immensely popular. Everybody wanted it. And it was shipped all over the place in Northern Europe and so forth. It was very expensive. And you can see how beautiful the glass blowers learned to work this material and make these lovely, whimsical, fanciful types of things, which also look very fragile. So, you know, when you shipped them, you probably had a lot of breakage. Well, the Venetians were trying to protect their industry, which was very lucrative, and their recipes were totally secret. And in fact, they prohibited the glass workers of Murano from leaving. But, you know, some people kind of smuggled them out. And eventually, in Northern Europe, they started to figure out ways to imitate cristallo, and they just called it crystal glass because it was clear, basically. And so in Northern Europe, you start to see, especially in the 18th century, a lot of this clear glass or crystal glass, and mostly tableware, but it's vessel glass for the most part. And it goes through different styles, starting from something similar to the Venetian style, more towards a Baroque style, kind of heavier, and they learned how to cut it and make facets and have it really sparkle. In fact, they got very good at these recipes so that it really rivaled the cristallo. They could have it locally, so they didn't have to ship it. And this kind of glass is either called Central European glass or Bohemian crystal very commonly. And you may know that, in fact, true high-leaded crystal glass was invented in the 17th century in England, and that is usually credited to a man named George Ravenscroft, and that whole story is very interesting, but I won't get into it. But he was trying to come up with an imitation of cristallo for the same reason, that it was just too expensive. And he actually did smuggle a Venetian to do it for him. He had been living in Venice and managed to get a Venetian glassworker to come, and he's probably the one that kind of invented this new type of glass that has an absolutely new recipe, and it was patented, but the patent doesn't say anything about the recipe, and they kept that a secret. So I've just shown here a few examples, also goes through a variety of changes in style. And by the time you get to French cristal, it took them over 100 years to crack the recipe. They had all been trying, but finally, in the late 18th century, they figured out how to make this high-leaded glass, but they continued to make something that would be more consistent with this Bohemian crystal. So I have two examples here of glassware that was made, probably all in the northeastern part of France that Carolyn referred to. And the earliest glass house that was making true crystal was the Saint-Louis Cristallerie, which is actually still in existence and became the official royal glassworks. So this finally, after my little whirlwind tour, brings us back to Laurent. And on your upper right, you can see an image of our beautiful Madison flute, which Carolyn told you about. And you can actually see that stylistically it has a lot in common with the type of tableware that was being produced at the time as well. So the patent says en cristal. So was that meant just like any type of clear glass? Well, we think that the fact that they mention how heavy it is does indicate that it probably was this much heavier lead crystal. But we have also dug up contemporary sources, and I found a source from 1800 of someone who was allied with the Ministry of Science, and they understood a lot about glass science at that time, and he says that crystal properly means high-leaded glass, and he also gives this percent range that I mentioned before. And we have a glass worker from a bit later in the century who says the same thing, that in France, apart from other countries, crystal means high-leaded glass. So we do think that the patent is intended to refer to this type of glass, which actually is quite stable. So then we have a question. Why did Laurent make two types of glass? Because we found that most of his flutes are in fact this other type of potash glass, which unfortunately is not very stable from deterioration from the environment when there is a lot of humidity around. And this has been an important focus of our study to understand that deterioration. But both types are dimensionally still very stable, and so that does satisfy the patent. We have questions we really will never know. Why did Laurent make these two types? Could be partly having to do with the weight, but it probably has a lot to do with the cost, because the cost of making leaded glass was much, much higher, and we know that also from contemporary sources. Is Madison's flute made out of true crystal? Possibly because he had to ship it across the ocean, and it was a little more robust, a little tougher. And Carolyn didn't mention this, I love this, but Madison forgot to send a thank you note. And
I was being generous to President Madison. I mentioned we had the papers.
Yes, and we have a letter of Laurent to Madison saying, "By the way, did you get my flute?" I'm sure he was worried about whether it survived the crossing. But in any case, I think, all of this type of investigation, and certainly the now a kind of missing piece that we have in this story of hearing the flutes and understanding their sound allows us to appreciate these flutes in this whole continuum of time, and especially in the history of flutes. I think we understand that they're very remarkable and not just novelties, as many people have referred to them in the past. And I hope that you'll see also from our technical study more of evidence of that, so I will hand it out to Dr. Loew.
Thanks a lot. Thank you, Lynn. Is that working? Yes, good. Well, to continue the story that Lynn began, I want to tell you something about how we looked at the flutes in many ways. And the first was physically to see how they were made. Well, they were carefully made, as we'll see in a moment. Here we have GW's skinniest patient being reassured by Carolyn that this will not hurt. And we were very fortunate to have help from our GW Department of Radiology to do a CT scan of this flute. And you may see that the R is on your left and the L is on your right, and that's because CT images are always viewed as if from the patient's feet. So the patient's right is your left, and so on. And what we're seeing, we're going through slice by slice through the CT scan from foot to head. And what you can see, among other things, is the constancy of the bore, the hole in the middle, and how it changes slowly as Laurent intended it. The flashes that you see are artifacts due to the metal keys that are on the instrument, and those are not imaged well by the X-rays. But you can see, for example, holes as they appear where the touch holes are for the player to use. And again, there we have a break between the pieces of the flute that you saw. And the idea is that we wanted to see specifically how this diameter changed. You can also see some of the hexagonal or octagonal structure, there was a touch hole. You can see the structure that we saw in Richard's flute of the fluting, the cutouts that were used probably to reduce weight. And so this tour through the instrument is showing us the great care that Laurent used in making it. Well, here on the left you have one of a Laurent flute that was part of the Dayton Miller collection. On the right is one held by a private collector. The one on the right was made in 1828. And what you're seeing in the graph on the vertical axis is the diameter, the inside diameter of the flute. And along the horizontal axis is the distance away from the head of the flute. And so this head joint is of constant diameter. And what's remarkable is how constant it is. As you can see across its entire length, the size doesn't change at all, even in tenths of a millimeter. If we go to the upper body joint, again, the Dayton Miller flute on the left, the private collector is one on the right. Here the diameter changes, and so you can see as you go from left to right down the length of the flute, the diameter along the y-axis is getting smaller and smaller, but with each change there's a very constant diameter held. The little dots that you can see indicate places where the keys were causing an artifact in the image. And so it's clear that Laurent really mastered the art, and it's still not known, a number of theories have been advanced, how Laurent was able to make this change in diameter so precise. Did he drill it, etc.? There were various proposals have been offered. Here's another joint, another section of the flute. Again, you can see the diameter stays constant over a certain distance, then it decreases and stays constant again. Again, evidence of very careful manufacture. Finally, the foot joint, the bottommost joint, we can see some artifacts in the image that reveal themselves in the dots that you see in the plot. But again, the constant diameter in this case, the diameter is increasing as we move down the flute. So just to summarize these, we can see this is the various joints, the various sections of the flute from left to right, the head joint, the upper body, the lower body, and the foot. And you can see the progression of diameter as we move down the length of the flute. Again, how constant and how smooth a change Laurent was able to create is remarkable. Here is a different flute. We see the same sort of behavior. Well, now we're interested, of course, in what these flutes were made of. And one of the ways to examine them, there were a number of ways, and I'm going to talk about each of these very briefly. We're looking across the electromagnetic spectrum, and the numbers that you see across the bottom are the wavelength in meters. And what we see as we move across from left to right, we're going to be working in the infrared, the visible, the ultraviolet, and then X-rays. So we're taking a fairly big chunk of the electromagnetic spectrum and examining the flutes using each of these kinds of energy. And so the first one is called X-ray fluorescence. You bombard the material with X-rays, and the material responds by emitting photons, bits of energy at various energies. And what we see in these plots on the vertical axis is intensity, and the horizontal axis is energy. The important thing about these is that specific materials have these peaks that you can see at various energies. So the top plot shows the response for two of the Dayton Miller flutes. The axes have been offset the plots have been offset so you can see them separately. But what you see, the two big peaks labeled PB for lead, are very strong and in the same place. Lead appears farther to the left as well in a bit lower energy. Clearly evidence of the lead composition of these flutes. When we look at 5 of the other flutes in the lower graph, what we see are energies that are quite different. Pushed far to the left, you have silicon and potassium and calcium. There are almost no peaks at lead. And what we have then is clear evidence of the potassium composition of those flutes. So X-ray fluorescence gives us an initial idea of what the composition of the flutes might be. Well, how does this reveal itself in other ways? Here we have two sections of flutes in a room light, in ordinary light. If we now illuminate them with ultraviolet light, black light, for example, at 365 nanometers, the one that is made of potash glows or emits, it fluoresces mostly in the green, and that's due to trace manganese that was part of the manufacture. Whereas the leaded flute on the bottom glows a pinkish color. And so a very simple tool, a little ultraviolet flashlight, for example, could perhaps, in many cases, reveal the distinction between those flutes made with lead and those that aren't. Well, then the question is, if these flutes in some cases are exhibiting deterioration, as Lynn mentioned, how can we characterize that? How can we describe the deterioration? So here is a flute. These are sections of the same flute, all made with the same recipe. And we can see that the uppermost joint, the head joint, is very opaque relative to the others. The hole that you see is the place at which the player will blow. And so the combination of spit and other things over time can accumulate and cause, we think, that seems to be the case, can cause the joint to become opaque. The second one down is not quite as opaque. The third one is an alternative joint that Laurent made that could be used to change the pitch, or in some cases to replace one of the other joints, and you can see that that's far more transparent. And finally, the one at the bottom is also, again, giving evidence of this opacity, indicating the beginnings, or depending on the amount of time, perhaps advanced deterioration. Well, so that was using just our eye, basically. If we go under a microscope and take a photomicrograph, in this case of the inside of the head joint of one of the flutes, we can see this pattern of cracking, polygonal network. And so this all by itself does indicate that there are some beginnings of problems inside the flute. And so this is now at the microscope level. If we go even further in resolution, you can see the 0.5 millimeter bar, the scale bar on the image. If we go now to a higher resolution using scanning electron microscopy, and now take a slice through the flute, and that's not exactly what was done, but a tiny sample was removed by our colleagues at Catholic U from one of the Dayton Miller flutes that was already damaged, so we didn't hurt a good flute. If they took this small sample, what you're seeing in the lower part of this image is a cross-section of the wall of the flute. So you see the outside and the inside, and then the body of glass. But what makes this interesting from a deterioration point of view is this so-called alteration layer that's about 30 microns, or 0.03 millimeters thick, on either side of the glass. And that's indicating real deterioration, which can in turn lead to and in fact there is evidence of cracking already beginning. So now we're looking using an electron microscope, and we can clearly see evidence of this deterioration. Another technique called optical coherence tomography, it's a long name, is available commercially and used principally in the medical field, for example, to look at the retina of the eye. The reason that it is used there is that it has very good resolution. It can resolve to 1/1,000,000th of a meter, a micron. And it uses light to do this, and it's a process of interference. 2 beams of light are used. One is a reference and one looks at the sample. They come back to the detector, and the difference between them is used to create the image. In the case of the eye, we can use this to detect very small changes in the layers of the retina, which can indicate early signs of disease. And we at GW have used OCT to look for early signs of bladder cancer. Same reason. We can penetrate into the wall of the bladder 1 or 2 millimeters, but at very high resolution, and see changes in the layers of the bladder. So it's natural then to say, well, why not use it on a flute? Of course. and so we did. And what you see here in the lower, recall that the flute, that's the section that's third down from the top, is the one that was relatively untouched or that was in very good condition. And you can see in the lower left scan, the slice that we see is relatively smooth as compared to the other 4 that show real signs of cracking, real signs of changes. And again, you can see the scale bar in blue of 1 millimeter. These cracks that you see are on the order of much smaller dimensions, on the order of a few tens, let's say, of microns, sometimes even smaller. So OCT is another way that these flutes can be examined, and clearly can show this kind of deterioration, perhaps earlier than some of the other methods. Now, another way that we can characterize the flutes has to do with what we saw earlier when we saw these alteration layers. The alteration layers represent hydration, the presence of water. And so FORS, fiber optic reflected spectroscopy, uses the reflected light and captures the light from an ordinary light source, a broadband light source, and measures in the near to shortwave infrared from 1200 to 2200 nanometers. That's the wavelength, and you can see going across the bottom of the graph. And what each of the curves is showing is the amount of energy received when the FORS instrument was used to look at various sections of a flute: the head, the upper body, the extra joint, the lower body, and the foot. And you can see in 4 of the 5 curves very sharp peaks at 1910 on the right and 1407. Those indicate the presence of water, and that's the early, or perhaps advanced, depending, signs of this hydration layer that in turn precedes the cracking that is of such concern. Notice that that extra joint of the black line, the third one down, does not have nearly as strong peaks. And so FORS is telling us that that one almost surely has no hydration present. So this is again, and I haven't used the word, but all of these techniques, except for the SEM, are non-invasive. We don't have to physically touch or take samples from the material. Well, let's look again at the microscope image, because what we'd like to be able to do is to quantify the amount of deterioration that we're seeing. And so if we take this image, we can see that there is texture there. And one of the things that we're very interested in from a scientific point of view, whether it's a flute or the texture of a CT image of your kidney, which we have worked on, is how to characterize the texture. Texture is something that we all know about, but when we're asked to describe it, we often find it difficult. So our colleagues at Catholic University made some sample glass for us. They used recipes identical to those of the Laurent flutes, which they got from these tiny samples that they analyzed. So they knew how much potassium, how much calcium, etc., was used to make each of the flutes. They made new samples, circular discs of these, using these various recipes. They were then taken to a chamber at the Library of Congress to do accelerated aging. So the chamber was held at 90 degrees centigrade, very hot, and 90% relative humidity, very humid. And the samples were aged for different amounts of time, with 1, 2, 3, and 7 days. So the sample was removed after each of those periods of time and examined, and you see the photomicrographs, in this case, of 1, 2, and 3 days of aging of these samples. So we clearly can see a difference between them. But what we'd like to do is quantify that. We'd like to describe it quantitatively so that we can then look at a flute, take a picture of it and say, this is just like the 3 days aged, for example, texture. So what do we mean by texture? And there are a number of ways we can describe it. We can compute statistics of the intensities of the image. We can ask, how does a given pixel, a picture element, relate to its neighbors? We can look for repetitive or pattern changes in the texture, and you can see evidence of some of that here, for example. So then what we did was to take an original image. We divided it up into a grid, taking small samples, small sections of each. Each of those sections then was analyzed separately, and we used for each of those samples, we computed some of the features that we have just described. And those features were then used to construct a set of reference samples. And those reference samples are what we could compare new samples to try to determine what the equivalent aging was of our accelerated aging. And we could do this with about 92% accuracy. So a new sample compared to our old was able to classify, we were able to assign an age quite accurately. So this idea of quantifying the texture is one that can be used in the future for new samples. Well, okay, so what do we do about all this? We can identify the problem. We can combine information from several sources, and you've seen a number of them. And the goal then would be to stabilize the flute and to prevent from further deterioration. Again, just to recap some of these, here are some of the ways that provide information to us, the methods, and some or all of these information from these would be combined to form a judgment about the flute. And so the goal is to allow what we've learned from fairly complicated research using sophisticated instruments to provide simple methods for museums and other holders of glass that don't have complicated instruments to nevertheless make an evaluation of their glass, which of their samples is in need of immediate conservation or special efforts made, and others are stable and don't require that. And so we've put together a decision tree. This is a simplified version of it. And you might, for example, take a flute, examine it with ultraviolet, and as we've seen, that can sometimes separate the potash from the leaded, and in some cases we're uncertain. We then might inspect it using microscopy or OCT or FORS, and thus allow us to classify the extent of deterioration. And then that in turn leads to a set of recommendations that our conservator colleagues can make about how do we store it, what temperature, what humidity, do we clean it, do we not clean it. And this then allows relatively simple tools to be used to conserve the glass. Now, I mentioned that a lot of this, I didn't mention specifically, but looking at texture, for example, we don't have quantitative descriptors. And the terms that glass conservators sometimes use, crizzling is one of them, is a very vague description of the surface of glass. What we'd like to do is find a way to take samples of glass and rank them from most to least deteriorated. And to that end, we're going to ask your help. So we have something that we've called a visual validation tool. And this was constructed by one of our colleagues, Nick Keevy, who's here with us today. And the idea is that we have pairs of pictures of glass. Notice that the scale is the same in both of the pictures. And we have, and our goal is to show you, and I'm not going to do it now, but I'm going to tell you how to do it, to show you a sequence of pairs of images and ask you to choose the one that you believe is more degraded. And then, and if you feel that they're the same, you just click on to the next one. We have put this visual validation tool onto our website called glassatrisk.com. And this website contains a lot of very good, I think, very good background information on glass and about the flutes and about the work that we've done. But one of the headings up at the top is called Help Us Assess Risk. And what we'd like to do is when you get home, please go to glassatrisk.com, click on that tab, which will take you to a different website that will show you pairs of images. And you simply tell us which one is you believe to be more degraded. And these will be collected, and we're going to then see if what consensus may exist as far as the deterioration is concerned to your eye. And that in turn will allow us to rank them and then go back and extract some of the measures I showed you and to try to relate quantitative measures to this ranking of deterioration. So please go home, go to glassatrisk.com, and don't go home yet, when you go home, and take our survey. So it's a pleasure to acknowledge all the people who have helped in this effort at GW, at Catholic U, at the Library of Congress, And this project has been supported. We are very grateful to the National Endowment for the Humanities for their support of this project. And with that, our panel is open for questions.
Thank you. I see a hand back there. Maybe stand up and ask a question.
Hold on.
Oh, sorry. Here comes your microphone.
So I really love this marriage over the centuries of music and physics and materials, because it resonates in many aspects with my background. I spent many years in the semiconductor industry and the materials technologies of building integrated circuits, computer chips that's in everybody's phone. And those are multi-layers of metal and semiconductors and glass. And there's a lot of surface science in the passivation of glass to not corrode and adhesion between metal and glass. And so the next step beyond identifying the glass at risk is the stabilization. And I'm wondering whether you're connected, and if not, I would be happy to connect you with the various silanes and polysiloxanes and various monolayer and sort of atomic layer passivations that won't affect the structure of the glass. It won't reverse the existing cracking, but may forestall any future degradation. So I'm wondering whether you've touched base with the semiconductor technology areas, which has all these passivation techniques at the sub-micron level.
Thank you. I'm going to take this one. Silanes have actually been investigated quite heavily in the cultural heritage science field. They've been applied to several kinds of materials, including stone and ceramics. We really shy away from some of these approaches until we have very rigorously tested the effects on an aged material. And that's really the difference between the kinds of materials that you find industrially, which are still very pristine and you can clean them and have very clean surfaces. And it's really what distinguishes our field and makes it so complex is that we have an aged surface. In the case of the flutes, it's already 200 years old. And it also has residues of polishing material, which we found. And it can have products from degradation. And it can have products that were introduced by the environment, from pollution and from human spit or fingers or whatever. So makes application of coatings very, very difficult. And so there's immediately an adhesion problem, but if the coating is not going to absolutely stop the process of deterioration that's taking place, then it can end up kind of trapping products that are trying to come to the surface, and then you get this kind of spalling or lifting off of the coating that sometimes can take things with it. So it can be very scary to apply new technologies. So silanes, I have to say, have not been very successful in some applications. But we certainly have been talking with our colleagues at Catholic University about possible things such as aluminum oxide coatings or other things that could be applied that might be able to stabilize things. It's just, it's a much more complex and rigorous process that we have to go through before we would dare to intervene in that way. So normally our approach is to stabilize the environment, to, if not stop, but slow down as much as possible the factors that lead to deterioration. In the case of glass, this is humidity. So we put things in the Library of Congress. We actually had an entire project and went to great expense to design special cases for these flutes that have extremely stable environments, so there's not cycling, so there's no drying and wetting and drying and wetting, which can contribute to cracking. That's normally a kind of safe approach. It's less interventive that we take in general for collections. Thank you. Yeah.
My question is a little simpler.
Maybe I'll take that one.
So I'm astounded by the consistency of the diagram from tube to tube. So my simple question is, how do they make the whole? How is the tube actually? Was it a boring process, or how?
Yeah, the report from that was submitted by Laurent early on said that it had been drilled, but we haven't come to our conclusions yet, right, Marie?
We have a raging controversy going
Yeah.
on about this question.
We talk about this a lot. It's amazing how perfect it is. I mean, he was superb at what he did too. It's astounding. Thank you,
Yeah.
Mary, for proving that.
Yeah, so we were totally astounded when we saw those CT scans as well. Because although, we could talk about drilling, we're talking about hand tools. These are handmade. So it is, and they would be difficult to work, the glass. We're still trying to answer that question, actually.
Anyone else?
From a sound quality point of view, which of the flutes that you played have the most stability in the sound and reproducibility over time? The wood, the glass, the metal?
Yeah, that's a very good question. The crystal flute, it took me quite a bit of time of practice in playing it to really find its sound. I refer to it as a playing that a couple of days I suddenly felt that I had found the sweet spot where the placement on the mouth, the speed of air. Of course, the fingering system is completely different from the modern flute. I believe probably not having grown up from my childhood days playing this flute, it's a learning process for me yet. I first, of course, been a player on the modern metal flute, what we call the BEM system flute. And my first attempts at learning the Laurent crystal were to sort of go from that backwards to it, and I found it very frustrating to go backward through history, as I think most modern players do when they attempt to play the Laurent or flutes of that period. But I also, some years ago, became very interested and became a performer on the 18th century flute called the traverso. And it occurred to me that the sound concept, as well as the playing techniques, developed from the 18th century into the early 19th century. And in fact, the early players probably were schooled on the 18th century flute. So I used that technique. I went the course of history into it, and suddenly light bulbs came off of my brain and things worked. And then I'm still in the refining process of discovering the sound. It's a quality of sound that is, it's different from anything else, and I like to think it's a sound which I'm so delighted to bring it to life again to you all, because it's been lost for 200 years. It's not like the old flute, it's not like the new flute. In some ways it's more stable in sound. The making of the flute is the intonation, the tuning process is different from the modern flute intentionally. The flute was not made in what we call equal tempered tuning. It was made in a different tuning system. So that takes a little adjustment on your ears as well as mine when I play. I hope that answers your question a bit, right?
So we have time for one more question.
Given that we've seen that moisture can damage the flutes, is there anything special that you have to do after playing to help preserve the life of the Laurent flute?
Well, Richard has a really scientific approach to cleaning his flute. He takes a chopstick and he wraps a cloth around it and he wipes out his flute. No, this is true, but I think he's done a great job with what he's been doing. And that's
It's an early 19th century chopstick.
We analyzed it actually, and it wasn't. It was later. No, but as Murray said, we did develop, or as Lynn said, it was not very expensive, a cabinet to store the flutes. So we have stabilized them at temperature, humidity, the supports and the materials that are around them in the cabinet. But we need to work on that next step now that we've done that step, and we're going to. And Richard's been really great and helpful in that regard. We've seen what he's been doing with his flute and how stable it's been. So we thank you for that and your chopstick technique. Anyway, I'd like to thank everyone for joining us today. My deep thanks to the music division, recorded sound division, the fine, fine talent of the preservation directorate, my colleagues at Catholic and at GW, and to all who have been as clearly captivated by these flutes as Dr. Miller. But before you go, it's not another test, but Richard is going to play a little encore for us, if you don't mind. It's a piece that is in the Miller collection and is dedicated to Laurent. It was written in about 1804, 1805. And he's going to play a little excerpt from it on his flute. Thank you. small display on stage with the flutes and the materials that I mentioned during my talk. If you would like to come up, just come up on this side of the stage in a slow single file. I'd first like to invite the chief of the music division and her guest, the French ambassador, and the staff from the embassy to come up first, please. And also, while they're making their way up, you might notice in your program a little Cupid playing the flute. And that was actually drawn by Dr. Miller in 1893 on Valentine's Day when he was making his proposal to his wife. And you will see that manuscript up on stage if you come up. Thank you very much.